All right, I want to thank everyone for joining us today for the Oasis Sales Did You Know webinar. We've been doing these all year so far on different topics. Today's topic is you may have signal integrity issues and not know it. One of the nice things about the Hyperlinks tool or some of the SI tools, that we have out there today is it's so simple to check designs nowadays with model availability or even be able to create models. So that's what this webinar is really going to cover, is how simple it is for those that think SI or signal integrity checking is a difficult thing to do, and it's really not. It's very easy, and some of your designs or most designs out there today may have issues that you're not aware of. So a little bit of my background. Again, my name is Brent Klingforth. I'm the application engineer for Oasis Sales. I've been with Oasis for about 13 years now. Been in the PCB design industry for about 20 years. Worked at HP, then did a lot of consulting for many years and laying out printed circuit boards. I'm very experienced from anything from the simple designs to power supply RF and high-speed digital. I'm by no means a signal integrity expert, but just even knowing the basics can assist you with doing a better job of designing your printed circuit boards. You don't have to be a doubly educated engineer nowadays to understand signal integrity. A lot of the principles are very simple, and the tools that you may have today, that's the other big thing I wanted to point out, is many of you may have some of the Mentor Graphics products like Pad Standard Plus or Pads Pro, and you have these tools in your toolkit. You just didn't realize it maybe, and you're not taking advantage of them. So let's go ahead and get started. A little intro about Oasis Sales real quick. We are the reseller for the mid part of the United States. We sell all of the Mentor Graphics products that involve electrical engineering, from cabling, FPGA tools, PCB schematic tools, simulation products, thermal simulation, and now we're also selling the Siemens products. It's as everyone probably knows, Siemens has acquired Mentor Graphics. We are also representing all the mechanical engineering tools from Siemens as well, Solid Edge being a big one of those. Again, the Oasis is pretty much it has the largest geographical area in the United States. We cover all the Midwest, a little bit of the West. And then we've been partnering here with Trilogic, which is the East Coast reseller for Mentor Graphics with these webinars. Many of you may be East Coast customers, and many of you may be ours. It really doesn't matter. We're all part of the team when it comes to Mentor Graphics products. So feel free to contact any of us and you'll be directed to the appropriate person. Like I said, we've done many of these webinars already. You can go to the oasissales.com website and click on events, and you can see all the previous ones that we've done, or you can go to our YouTube channel, which I'll talk about here in a second. Our next webinar, just so you know, is coming up on November 9th. We're doing these about every 30 days at the beginning of the month, typically. This one's going to be on library management and how it doesn't have to be that difficult. Many people feel that this is the hardest thing to do, and starting to use a new tool or working with a CAD tool in general. And we'll talk about how that can be streamlined and simple with the Mentor Graphics products anyway. So, and as I mentioned, Oasis Sales is very active in their YouTube channel. We post all of our webinars out there that we record, and we've added additional ones from Siemens and Mentor Graphics. So it can be a kind of a general place for you to go find stuff. We also feature featured channels, Mentor Graphics and Siemens as well. But we'll send you a link after this webinar as well to our YouTube channel where this video will be uploaded. I'm also going to place a bunch of links in the notes for this webinar to other webinars that Mentor has conducted on their website that might be of interest to you, like other signal integrity related webinars that are really good, that go into maybe more detail than what I'm going to be talking about today. So if you need any help with anything, you can contact me. I'm, again, the application engineer. I'll help you out with any technical issues that you may have, but I'm also available to do on-site visits if you'd like me to come visit you and go over any of the topics related to Mentor Graphics or even Siemens. Be more than willing to come out and visit you, especially if I'm in your area. And I usually try to contact a lot of our customers to see if they're available when I'm in a location near them. So if you have any questions to ask, please use the go-to meeting panel. Down the bottom, you'll see a little chat area where you can type in your message. It should only go to me. At the end, we'll have Q&A, but feel free to type in a question while we're going through the seminar. And then I'll answer those questions at the end, unless it's something really quick I can throw out there while I'm talking or speaking. So let's go ahead and get started. So just real quick here, I'm going to go over a quick presentation. And then as I go through this, we'll be showing the tools that you can use and to do signal integrity simulation and how simple it really is. So this is one of the big questions or the big answers I always get back when I talk to customers about, are they interested in doing signal integrity? Everyone says, well, we don't have any high-speed signals in our designs. Our highest frequency is 12 megahertz, 20 megahertz, 50 megahertz. I don't think that any of that would cause issues regarding signal integrity. And, many years ago, that was probably the case. I mean, I'm talking like 10 years ago. But and many say, oh, we don't have any signals over 100 megahertz, because a lot of people think that when you start getting up into the 100+ megahertz range, that's when signal integrity issues start to arise. But that is 100% not the case. Signal integrity is not induced by frequency alone. It's really induced by the slew rate or the edge rate of the signal. And even a 12 megahertz signal can have a fast edge rate and cause signal integrity problems. So it's not clock speed, it's edge rate. 300 picosecond switching edge rates can cause a lot of issues very quickly. In fact, anything from 5 megahertz or 5 nanosecond edge rates on down and faster will start to induce problems. But here's just a real quick example of a 300 picosecond edge rate signal on an 8-inch line with a ground plane reference nearby, and how that signal causes problems as far as ringing and overshoot. Now, granted, 300 picoseconds is not what a lot of people are probably dealing with out there, but the point is, if we were to use this as a clock where the edge rate was 300 picoseconds, but the frequency we were switching was only 10 megahertz, we didn't think, oh, we're not going to have any issues. You'll see that you are having problems because it all is induced by the edge rate of that signal, not the frequency that you're using. And one of the biggest things I'm going to point out in this webinar is that a lot of modern day chips that you're buying, even simple little PIC processors or TI or little ARM processors that are inexpensive that you're starting to put in a lot of your IoT products out there today, are going to have fast edge rates, whether you like it or not. Now, there are ways to control that in some of these smarter devices nowadays, but this is to really inform you that what you're doing today needs to be changed. So some of the sources for signal noise are going to be reflections and distortions. That's the big thing that causes signal integrity problems is as a signal edge starts to become faster and faster, the impedance mismatches on that transmission line and with the receiver cause distortions or reflections, okay? So a lot of it is all stems around impedance discontinuities. And there's a lot of information you can get out there on the internet now to understand this, and some of the webinar links I'll have more information on this, but this is really the big part of what causes signal integrity. Some other issues you can run into with noise is just crosstalk between nets, capacitive coupling or inductive coupling between nets routing next to each other or over the top of each other. Obviously, those doing multi-layer boards with inner layers routed next to each other. Hopefully, if you're a board designer or electrical engineer, you understand that you should never have traces running right over the top of each other for adjacent layers, because that's a huge capacitive coupling mechanism, which causes major crosstalk problems in your designs. But that's, hopefully everyone understands that. Another issue that's becoming more and more prevalent today is the low power devices. More and more devices are running at 1.8 volts, 3.3 volts, and you can start having issues with voltage drop in your power rails due to switching devices if you're not, supplying enough current to those items. And I'm going to talk about a tool at the end that can assist in this area. And then, of course, EMI issues can put noise on signals. So we have to do our best to make the signals as clean as possible from our end, what we have control of, because some of these other things like EMI, noise being introduced by surrounding objects, are going to affect our noise margin and cause additional noise. So if our signals are already ringing really bad, any additional noise is just going to be amplified by that. Plus, EMI can be induced by signal integrity, believe it or not. So what are the effects of signal integrity problems in your design? The biggest thing is that you're going to have a hard time distinguishing or figuring out why one of your designs may not be working. And it could very well be induced by signal integrity. So random glitching could be occurring, just data rate failures, data errors when you're doing your testing can all be induced by signal integrity, and you may or may not realize this. A big one with that as well is you may test stuff in your, in the office or the lab under certain conditions and everything works fine, but these devices nowadays are also very temperature sensitive. So as the temperature rises or falls, it changes how the devices function, which any signal integrity could be amplified or made worse just from a temperature change. So your product may have large field failures. This could also be induced by signal integrity. Again, you never know how your device is going to be used out in the real world. You try to do your best in engineering to reproduce those scenarios, but you still never know how something's going to be used by an end user. Noise on signals surrounding other devices, excessive current draw can be induced by signal integrity. If you have a lot of overshoot and ringing, you can induce excessive current draw by some of the components. Products may fail emissions. A lot of people don't realize that signal integrity can be a big cause of SI problems out there, especially if you're a new engineer coming out of school and you don't have experience in the real world yet. You've only been, discussing theory or working with theory. Is that any high frequency ringing is obviously high frequency, so it's going to induce or work outside that frequency range that you're expecting when you go out and do emissions. So the less ringing that we have in our designs, the more likely are to pass emissions testing. Interference from surrounding PCBs, you can cause interference in other designs. And another one people don't necessarily realize is that you can really cause part failure over time. If you look at a lot of the specs for components out there nowadays, they'll actually give you information in the data sheet that says, well, if this part anomaly works at 3.3 volts, but it's tolerant to 5 volts. But if you sit there and you keep hitting receivers with 5 volts, it can degrade the part over time. In fact, the part I'm going to be kind of playing with today showed that any excessive hitting of the rail of 5 volts, the part may only last for about 10,000 hours. When you think about 10,000 hours, that's a long time. But if you really sit down and think about it, if that product is on 24/7, 10,000 hours is about 18 months. After 18 months of constant use, your product could start having field failure issues due to a part being damaged from signal integrity. Again, I mentioned EMI, delay errors, getting timing problems due to crossing logic levels. And then due to multiple receivers on a line, you can get ringing in the transition area of a signal, which can obviously cause a lot of these issues as well. So some basic principles. Remember, I've already mentioned this once already, and I'm probably going to continue to mention it. Edge rates are the problem with signal integrity. So don't ever think that just because you're going to be using a part running at 12 megahertz that you're not going to have problems. And that's what I'm going to show today, is how I can switch a part at 12 megahertz, but I can still have issues just because the edge rate is too long and the traces on my board are 2, 3, 4 inches long. Most active devices today will more than likely cause SI problems. And this is just inherent with technology nowadays. IC vendors are continuing to reduce die structures, going from 100 nanometers. We're reaching what, 6 nanometer die structures nowadays. Of course, they can control some of this on the output buffers, because that's what we really care about from a signal drive standpoint, is the output buffer. We don't care about what's internally to the IC itself, but inherently in the process of manufacturing die, you're going to have FETs, output driver FETs, that are switching faster than you think. And manufacturers can control this. Yes, you're right. That's probably one of the big questions. Well, the IC manufacturer can control slew rate and slow down the edge rates, and they do to some respects. In fact, the part I'm going to play with actually gives you an option. It's a little microprocessor that many of you may be using today that has different output currents that you can choose from, which is a biggish part of how signal integrity can be controlled, is how hard you're driving that signal down the line. 2 milliamps, 4, 8, 12, 24 milliamp drivers can all make a difference in signal integrity as well. And you can play with some of that on these devices, but some you can't. Again, the main issue with signal integrity, it comes from impedance mismatch. All right, so the trace that's on the allowing the signal go from the driver to the receiver end of the IC that you're using. You can't control the input impedance of that IC that you've chosen. It is what it is, but it may not match, obviously, what the output impedance of the driver chip is producing. And you may think, oh, I'm not switching at high frequencies, I can just do a 2-layer board. And again, those are some of the examples I'm going to show. Is a lot of 2-layer board designs out there more than likely have some or minor SI issues that could cause failures down the road. So the PCB Stack-up, you have a lot of control over this. You can do whatever you want here, pretty much. A lot of people will try to make, you're producing stuff in high volume. You don't want to have a 4-layer board. You try and do it in 2. But realizing that the simplest fix for signal integrity issues can just be adding a power and ground plane into your design. You can almost guarantee that you're going to not have SI issues if you just do that one thing alone. And again, I'll show some examples of how that works. Driver strength is another cause of signal integrity. I mentioned that already in the first point, that a lot of these chips you're using nowadays, you control the output drive current, but a lot of simple logic devices may just be stuck at 12 milliamp drivers or 8 milliamp drivers, which are actually pretty strong nowadays, especially when you're in the 3.3 volt and 1.8 volt range. And that can increase your signal integrity issues that you might be having. So a lot of this stuff you can look at on the specifications, make sure you're checking out that data, because you can very simply do some testing real quick by downloading IBIS models to check it within hyperlinks or another signal integrity tool. So net topology is another big one for signal integrity issues. If you have like a clock chip or a device that's producing a clock line that goes to multiple devices, each one of those devices can have a different input impedance. And plus there's the delay from when the signal hits one chip to the next. and it causes reflections at different times, and that's when things really start getting messy. So anytime you have a multi-drop net with more than 2 pins on it, basically a receiver and more than one, or a driver and more than one receiver, you really should be playing or looking at topology, because even a 10 nanosecond signal could have issues based on net topology. And again, I'll play around with some of that here. So reduce impedance mismatches. There's things you can do for free. You don't have to pay really any extra money unless you're going from a 2-layer board to a 4-layer board. But just understanding that trace impedance alone can be a big problem in signal integrity. So you can play with your board stack-up, right? So being able to analyze your board stack-up long before you ever go to the PCB design or produce even your first prototype. Playing around with trace widths to control impedance. Obviously, you need ground planes or some type of reference. I should say reference planes. I shouldn't keep saying ground planes, because it's really a reference plane, whether it's power or ground. The return currents are going to flow on each one. So playing with trace width to change the impedance of a line can assist with signal integrity and reflections. PCB materials. A lot of times you just go with the plain old basic PCB materials, but there's a lot of other materials out there that may not cost a lot more, that could help substantially with signal integrity. So basically, changing the dielectric constant or changing the thickness between layers can be a big help in signal integrity. And trace length matching. The reason I put that one in there is if you have multi-drop nets, you really need to start paying attention to length matching, because the more the receivers are at different lengths from the driver, causes the reflections to happen at different times, and then you start ending up with a lot of weird ringing or reflections back to the driver, which causes induced high frequency content on your net. So like we always come back to the clock network. If you're using one chip to distribute a clock to multiple devices, you may want to put a series terminator in and then do a star pattern configuration from that resistor to each of those devices, and make sure you length match the nets within a certain distance of each other to reduce the reflection time delay differences, and make the signal as clean as possible to those devices. So playing with trace length, it can be a big help. Something not a lot of people think about. Controlling impedance mismatches with passive components. This one can obviously cost a little bit of money to use this function, but it's the #1 way to fix or reduce signal integrity problems on your board. The most common is a series resistor. For a single driver receiver pair, putting a series resistor in is almost a 100% fix in solving your SI problems. If you have a multi-drop net pin configuration where you have multiple receivers, you can go to an AC or DC termination, and these are those examples on the nets. These ones obviously have more parts involved. Some of them can be power consumption heavy. You got to be careful with DC termination. If anyone's done any DDR1 or 2 designs of the old, that was the #1 way when using DIMM sockets, was to use a DC terminator at the end on a multi to assist with termination. Most DDR devices now have changed these days. The 3, 4 devices really don't require that anymore. But there's other concerns that happen because the signals are switching so much faster than previously. So keep this in mind. When you have a multi-drop net configuration, you may have to put a resistor capacitor at the end of it to help control reflections. It just changes, again, that impedance at the end of the line, so you're not getting the reflections as bad in the end. The whole idea of the passive components is you're just trying to match the impedance from the driver to the receiver. When you have a series resistor, and your resistor at the receiver that goes to ground, you have a voltage divider. So you have a basic impedance matching circuit at that point. All right, this is probably one of the second biggest thing that people are worried about when it comes to signal integrity analysis is, well, I have to have a model in order to do it, right? I mean, you can't just go into an SI tool and drop down a receiver and a transmission line and go for it. You got to have some information about what the signal looks like that's going to drive the circuit, and what the receiver impedance information is going to look like. There are multiple ways to get this information. You can find models very readily now on vendors' websites. Just about every IC manufacturer's website will provide IBIS models nowadays, just because they know their devices are switching faster than they were 5-10 years ago. The tool that you're using may come with a large library, like Hyperlinks comes with a fairly substantial library of standard logic parts that you can choose from. You can create your own models from a data sheet. The tool you may be using would have a application inside of it that allows you to create a model, either just for a single pin or for an entire component you can use in your design. So doing something even with an estimated rising and falling edge and a receiver end is better than doing nothing at all. So even using some of the simple models provided with the tool, or using a model from a part that's similar to the one that you're using from that vendor, if they don't have one for your exact device, using a part that's similar could still give you more information than just doing nothing at all. So don't be afraid to try different options there. And then simple modeling. Again, if you just want to create a simple model of a pin, that is possible in most signal integrity tools, so that you can at least get some idea. Just give me a 3 nanosecond edge rate with some basic output impedance, so that I can check, my structure on my board to make sure my stack-up's going to be fine and my impedance of my traces is going to be fine. And then a lot of this stuff is very simple, and I'm going to show that here through demonstration. So PCB Stack-up is another one that you should be playing with. Don't wait for your fabricator. A lot of designers will go to their fabricator and say, hey, here's what I want to do. Can you tell me, what my stack-up needs to look like? Or you just blindly create one, put it on your fabrication drawing and say, here's what you want them to do. You spec out different basic material, but you never know what the performance of your board is really going to be unless you check your stack up yourself for impedance. And if you have any signals with edge rates over 5 nanoseconds, there's a good possibility you're going to have problems. And most of the ICs out there today are running with slew rates that fast. So the online free impedance calculators, a lot of people say, oh, I just use one of those to calculate impedance. Well, it doesn't give you the true story of the impedance of that net. It may not take into account all the fabrication processes that happen, the etching, etch back, solder mask over the top of a trace changes the impedance. When you're doing a strip line structure, you're doing a micro strip, obviously the materials, how close you are to planes. You can play with a lot of that stuff with the free tools, but you just can't get the full story from that unless you use a real stack-up editor application. Information needed for the stack-up design. You are going to have to go dig up some information. There's things like dielectric constant of the core materials, prepreg, and solder mask that you're going to need to know in order to really get a good idea for impedance and to do simulations with. But a lot of that is, again, very readily available nowadays online, or you can contact your fabricator and just say, hey, what materials are you going to use for the boards that I'm going to be sending you? And they should be able to give you the specifications that you can then enter in to a real stack-up editor application and simulation tool. And if you're doing really fast designs with really fast edge rates, you're getting into the gigabit transfer rate, DDR type stuff. Then you have to start worrying about loss tangent, which is something you can enter in most stack-up editors, because you start getting a lossy effect in the PCB materials as the edge rates get even faster and faster. Like anything over about 300, 250 picosecond edge rates, this becomes a big factor to you at that point. So, all right, let's go ahead and play around with some of this stuff before I'll continue and come back to here. So, I'm going to be using hyperlinks in this case because, you know, we are representing Mentor Graphics here. So if you're a PADS Standard Plus or PADS Professional, or you just own hyperlinks for that matter, or you can go off and just buy hyperlinks. Or we have options out there for any of you that are using Altium or Cadence, Eagle, any of the other even free PCB tools out there. You're not like you can't do signal integrity. We do have low-cost versions of the hyperlinks tool. Of course, we have our high-end stuff too that you can buy to do signal integrity with. So I'm going to open up hyperlink standalone here, and then I'll show you, obviously, for those that have our PADS flows, how you can go about integrating it. But I'm going to do a new design, a new schematic. This opens the tool up in our schematic entry-based application, where we can kind of do what-if stuff. So that slide that I was about to go on to is how you as an engineer doing the schematic can start doing or playing around with some signals before the board layout ever gets started. And I'm going to show you how to integrate that with DX here. But just real quick, I want to create a simple little schematic. I'm going to drop down a receiver, transmission line, and I'm going to put an output on that. Zoom in a little bit here. Connect these guys to each other. Let's just play around with something very simple. Double click on this guy. I can add a model to that. Again, I'm going to use just a simple model that comes with this tool. So I'm just going to play around with a 5-volt signal right now, output. And then I'm going to do the same thing here. I'm just going to make this an in. Click OK. So there we go. We have a simple driver, receiver, transmission line structure. If I double click on the transmission line, right now it's automatically set up for a stack-up scenario. When you open up hyperlinks for the first time, it just gives you a very basic 6-layer stack-up. Very common in PCB design nowadays. But I can sit there and play around with anything. I can do a simple where I don't know anything. I can just set the impedance of the line, delay. I can do a microstrip structure. I can do a buried microstrip, which is actually what everyone is doing, whether you believe it or not, because the solder mass that goes over your trace has a dielectric constant to it and can affect the impedance of that trace. Okay, so let's just play around. Let's just do a simple transmission line here. I'm going to set the impedance to something rather large. This would be if you're doing like a 2-layer board, there's no reference plane for your traces on the board, pretty much. So the impedance of your line is going to be quite high, and this is about what it averages, about 400 ohms typically. The delay would just be the length of the line. I'm going to do 150 picoseconds. So that's 150 nanoseconds, 0.15. That's basically a 1-inch trace on a typical board. Actually, it's about 175 for an external trace. Let's do that. And then you could set a DC resistance of the material if you want to. All right. And if we just go to the scope real quick and do a simulation on this, I'm just going to do a rising edge. Change that real quick. We'll look at our signal here. And we can see, let me turn off the driver. There's the receiver. So just a simple 2 nanosecond line at about 1 inch trace. You can see I've got a little bit of ringing in there. No, it's not a big deal. But how many designs are you doing today where your traces are only 1 inch long? Okay. So to show this a little bit quicker, I'm going to go ahead and do a sweep mode analysis. I come in here and change let's sweep the time. Let's go from 100 picoseconds to 100 picoseconds to about 800 picoseconds, which is about a 6-inch trace. And I'm going to go in 100 picosecond increments. And we'll see how the signal starts to producing more and more ringing as the trace obviously gets longer. So run sweep, start. Okay. So there you go. You can see as the trace gets longer and longer, you obviously start inducing more and more ringing with a simple 2 nanosecond edge rate signal, okay, which is quite common nowadays in a lot of the devices that you're using on your printed circuit boards, okay. So that 800 picosecond signal, which is about 1 inch or 6 inches long, we can go to something a little bit more common, maybe 400 picoseconds. You can see coming here, I can measure the overshoot, and I'm getting about 700 millivolts of overshoot on my signal. But again, if I look at this and even go with a 12 megahertz signal, change the duty cycle a little bit there, and whoops, increase that a little bit. We'll see that, yeah, the signal's not, frequency is not that fast, but obviously I'm starting to have issues when I start getting into longer traces on my board, okay? And these are the things that I'm trying to educate people on in this webinar, is that you may not realize it or not, but these are the types of things you could see on your board. If you're not looking at the digital signals on your PCB for signal integrity, these are the types of things that could be occurring and you don't even realize it, okay? So this scenario that I put up here is for like a 2-layer board. The impedance of a trace at 400 ohms would be like a 2-layer printed circuit board, okay? But just by going to a plane structured board, where let's go to the stack-up, I'll start with a 1/2 inch trace here, 6 mil trace. You'll see the impedance has dropped dramatically. It's 83 ohms at this point. Okay, click OK. Now I can go back into sweep mode here and play around with the transmission lines again. I can go from 1 1/2 inch to 6 inches, and let's go in 1/2 inch increments and see what happens to the trace at this point. So run sweeps, turn off previous. So there you can see with the same model, same edge rate signal, just by adding a ground plane, basically changing the impedance of that line, I have almost eliminated the issues with my PCB, okay? So if I go to my 3-inch trace, just by putting a simple plane in the board, I've solved my problem. Okay? I don't have to really do anything else at that point. But this, again, is what a lot of people don't understand, is you're trying to do 2-layer boards to reduce the cost of their product. They're routing the power and ground on the board. You may put power planes on the top, or a ground plane on the top and the bottom, but it's not a very good reference because it's so far away from the reference trace. Plus, you're more than likely crossing other traces, and it's not a consistent reference plane. You need a very consistent reference plane in order for your signal to look this good, okay? So again, something as simple as just putting a plane in a board can solve all of your signal integrity issues, okay? Now, obviously, if I start getting to faster signals, if I go to, let's try 3.3 volts, a fast signal here. And I'll switch this one to a similar in. Okay, and let's do the same simulation now on this guy. Wow. just by increasing the edge rate just a little bit. Let's go back to the 1/2 inch signal here. Oops. Yeah, I want to look at the receiver. All right. So there's the receiver at just a 1/2 inch. And if I look at the edge rate real quick on here, this one happens to be pretty fast. This is 400 picosecond edge rate. But now you can see as the edge rate starts getting faster and faster, the trace length is becoming a bigger and bigger issue. So everything is all about that edge rate. And most printed circuit boards, as the slower the edge rate gets, the impedance and everything of the trace on the board just looks like a lumped RLC network instead of being an impedance mismatch in general. So even if I had a 1 nanosecond signal, I'm going to start seeing problems. So here's a 1.5 inch trace, which is probably an average trace on most printed circuit boards. I'm switching at 12 megahertz, but this design is definitely not going to work. One, I'm driving to that 5-volt rail limit, plus I'm inducing a lot of high frequency in my design. I've got signals that are actually crossing the switching threshold, which would cause time delays or data errors. So again, these are the things that you really need to think about when you're designing your products. Okay. All right. So that was just a real quick example. Let's play around with the stack-up stuff a little bit. So as I mentioned in here, there's a lot of things you can do with your stack-up, more than just doing a quick impedance check with a calculator online. So in here, again, things are very important when it comes to the solder mask, the material you're using, how thick it is, the dielectric constant. So here's a simple 6 mil trace with a 10 mil distance to the plane and 1/2 ounce copper. That actually should be thicker than that because no one ever uses 1/2 ounce copper. External layers are typically 1.5 ounces when you take into account plating. But I forgot, let me go back to 0.5 real quick here. So you'll see the impedance there was 83 ohms, by just going to 1.5 ounce copper, that changes to 78 ohms. Again, getting closer to something that driver technically wants to see and helping reduce that ringing and overshoot. The dielectric constant may be 4.3 is quite average, but a lot of materials out there, it's around 4.8. You could choose materials that get you down to say 3.8. And again, you can play around with that impedance of that trace just by changing the dielectric material. Solder mask is typically about 1 mil thick on the board. Average dielectric constants on those is around 3.8. And you can see again how that affects the impedance of the trace. Okay, so if you're definitely doing any impedance matching, you need to make sure you take that into consideration, and some of those calculators online don't provide that. Distance to the plane, if we start playing around with that, obviously that's the biggest change in your impedance, is how far away the reference plane is to that trace. Okay, so if I go back to 4.3, I can tweak the impedance a little bit more with that. I can tweak the impedance by putting different layers or pre-preg materials in. And again, this is where you want to contact your fabricator, find out what materials they have available. Most fabricators have anything available from 2 mils, up this, however large you want to get. But it's probably more of what they have in stock on hand that's going to assist you with the cost of your product. All right. Something else to think about in design is this is a basic, simple 6-layer board stack-up, but one of the advantages that you can have of putting power planes in your board is actually using the planes as a way to control power supply noise. Okay. So yeah, you might want to do this for design, but you also may want to add 2 more power planes to the internal layers, especially if you're getting into higher frequency designs. For the simple stuff I'm talking about here that most people are doing, this would work great for a 6-layer board. But even on a 4-layer board, you may want to consider putting the power and ground planes closer to each other, because that induces a lower capacitance and therefore helps reduce any noise on your power planes, instead of using decoupling capacitors on a board. So people doing really high speed design actually use the power planes as a capacitor, because it increases their frequency range, because capacitors that you put on a design can only handle so much. And you need to capacitance levels that the device you can put on the board just can't achieve. Plus you start running into inductance issues. There's all kinds of other weird things that start to happen when signals start getting really fast. But for most of the stuff I'm talking about here and the average design a person's doing, play around with things like putting the planes maybe closer together can help with your power supply distribution network in your board. But in a tool like this, I can play around with all the dielectric information. I can add layers on the fly. I can do insert above and below. I can put more layers in. I can play around with metal characteristics in the design. You can do Z-planing for differential pairs. So if I have a 50 ohm differential pair on the top of the board, the tool will tell me what trace width I need to work with and what gap that I need to play with. Go to manufacturing information and you can play around with the fabrication trapezoidal or the etchback that can happen in a printed circuit board. In fact, I can enable that here. Now you can see what the etch factor is going to do and how it can induce or change the impedance of your trace. For most people doing the standard designs I've talked about, this may not be a huge factor. This becomes a bigger deal when you get into really high speed edge rates. Again, and then you have custom views where if you want to do everything in one view, you can play around with that. But again, the advantage here is I can move layers around, I can add layers, remove layers, play around with the thicknesses between the layers, get a visual aspect of that. I can even output that documentation, so I can print a picture of it to put into a document if I want to document this information, all from this tool. So again, anyone that is out there using the pads suites like Standard Plus and Pro have this capability, so you should be using it and taking advantage of that. Okay. All right, let's close out of here and go to a little more real world design. So here's a reference design that I actually picked up that's using a TI processor, a TM4C device. Some of you may be using this. It's quite common out there for doing a lot of simple DSP related designs where you just need some microprocessor horsepower. A PIC would be another one. They're quite common. But let's say I'm the engineer, I'm capturing the schematic. I want to play around with some of, I want to check some of my lines just for the heck of it. So I found the IBIS model for this out on TI's website. I added information to my design here so that the tool automatically knows what models to go get. I'm just going to pick one of my data lines here, and I'm going to launch this right into LineSim. So I can investigate if I need to worry about stack-up or anything on this device. So let's move this out here, change this guy to an output. Zoom in on that. So again, I'm doing kind of the same thing I did there before. We come in with our simple 6-layer stack-up design. Let's say I'm trying to do this in a 2-layer board for some reason. I'm going to go ahead and remove these internal layers, and I think you all know what's going to happen here. In this design, let's put 60 mils as the core to give me roughly an 062 board. Click OK. Right now the trace is 3 inches long. I'll leave it at that for the initial simulation here, but we can just go ahead and something else I wanted to point out with this model here, they give you the option of changing the output driver so you can control it. So in the model selector here, I can control what my output buffer is. Okay, not sure what TI defaults this to in the device, but I'll play around with each one of these so that you can see what the difference is. So first we'll do a 2 milliamp driver, click OK, do a quick simulation here of a rising edge, hit start. So very quickly I can see that, that's not a big deal. I do have some ringing on my line here. This may or not be a big issue, but notice there's that's high frequency content. So you do have to worry about that. We can measure the positive overshoot real quick. It's telling me I have about 385 millivolts. It's peaking at about 3.67 volts, which according to the spec is not a big deal for that part. It's completely doable, but that's using a 2 milliamp driver. What if I don't use that? What if I feel I need to drive the signal a little harder because the trace is going to be longer? So let's go back in here and change this to 8 and see what happens. Hopefully most of you out there can guess what's going to happen at this point. Start my simulation, and wow, just from changing the driver strength from 2 milliamps to 8 milliamps, doesn't seem like it'd be that big of a deal, right? But now we've induced a tremendous amount of ringing and overshoot in our board or in our design, just because we're trying to get away with doing a 2-layer board, and the signal, the impedance of the trace is just too large. Okay, so we're getting up to that 5-volt rail, which could be a problem. The part, it can tolerate it, but you're going to reduce the life of your part. We're inducing a lot of high frequency ringing. Let's say I wanted to run this part at 24 megahertz, which I think is its maximum. Do a simulation. Yeah, it may or may not be a big issue, but you can see here I'm actually crossing a timing threshold, and I may probably start getting data errors if I have a signal that switches that fast. So again, you may not think this is going to be a problem in your design, but it definitely is in the case of this scenario here. So let's go back to the stack up. I can add in those 2 layers back in again. So let's see, add below. I'm going to put in a plane, and here I'm going to add another one above. Okay, so now I have a plane in there. Let's distribute the thicknesses here a little bit. We'll do 20, 20, 20. So we're roughly at that 062 number. Let's change our solder mask to 1. It's something a little more realistic, 1.5 here. All right, just let's see what happens now just by putting planes in a very symmetrical layout structure or PCB structure. So our impedance of our trace has obviously dropped dramatically. But now let's go simulate that again. Hit start. So there you go. Just by adding a power ground plane in, I haven't completely fixed my problem. There's still quite a bit of overshoot and ringing in here, but I've reduced it dramatically to where the design is more than likely going to be a much more solid product in the end, especially when you consider in temperature variations, part variations that you're going to see from the manufacturer. So, okay. Some of the other things you can play around with is the big one is termination. Again, very simple to do. So I can come up here and grab a resistor, drop that resistor in here. Now I could sit here and click on this part and guess on values, but I don't want to try and do that. I'm too lazy. Maybe I don't know enough about the receiver device. So we can use something called a termination wizard. This is going to analyze your impedance structure for you, and it's going to pick a value. And I can say, I want to do that within 1%. I want to apply that value to this device, go off and simulate that again. And lo and behold, we have a perfect looking digital signal on our board. Now I could have done that probably with the 2-layer board and reduced the ringing dramatically as well. It just all depends what you're looking for. But you know, I could get away with probably removing this, changing the stack up even more, making the layers between the planes to the traces thinner as well. So there's a lot of things that you can play around with, but that's the whole idea of what I'm trying to convey here, is that these are simple things that you can do, but you have to have a simulation tool to understand this and to do this, and how simple it actually can be. It took me a couple minutes to set up that simulation and go off and run it. Okay. So let's exit out of here. Last thing I want to point out real quick is if I go to the layout, here's the actual layout for this printed circuit board that I've done. Let's say I've ignored everything I've talked about already, and I've just went ahead and designed this printed circuit board. Okay, I'm just going to go ahead and you can click on a net and kind of see where it's routed. But again, for those out there using some of the pad suites, I have these signal integrity tools. I can launch this design into hyperlinks and play around with some of these signals to see what's happened based on how I decided to route this board. Okay. Take just a second here to load this. So there's our design. Okay. Let me zoom in down in this area. This is the device that we've put on here for test. I can select nets in here by simply grabbing it and selecting it, or I can go to the net selection, which is probably a little better way to do it, because I can sort my traces by length here. So I can maybe go to some of the longer ones like this PB2 net here, which happens to be 2 inches long almost. Now, again, I think most of you can probably understand what's going to happen here. This is a 2-layer board. I tried to do this in 2 layers. That trace is 2 inches long. It's that same part that I just experimented with in the schematic tool. Let's make sure we have models set up. So again, my information transferred across from the schematic into the PCB. So in here, I already have the model information set up. I can go in and set up the driver output strength if I want. I'm going to leave that at 8 milliamps in this case. Go in again and do my simulation now. Do a rising edge, change my scope here, and lo and behold, exactly what we saw previously. I thought this was going to work just because I didn't think the edge rate of the signal was fast enough to cause a problem. But here we are again, a lot of ringing induced in the design. Okay, yeah, I can play around and try to fix this. So one of the things I can actually do in here is I can say, okay, well, what if I put a terminator in here? Without going back to the schematic, I can actually add this device in here on the fly. So I'm going to add that. I can use the quick terminator tool again to come up with a value, apply that value to my part. So on the output driver here, imagine a resistor sitting here now of that value that we just calculated. Let's go off and simulate this again. So yes, by putting a simple series resistor in there, I can stick with my 2-layer board and solve my problem. But again, I wouldn't have known that if I didn't have a simulation tool. I could have produced my prototype and things would have been working. I would have had to spend all the time to do a redesign, get a board fabbed, assembled. I wasted a bunch of money and time not knowing that I had signal integrity issues because I didn't use a tool that I may have had already. All right. So again, those are some quick examples of how simple it can be to simulate a net or a design in a signal integrity tool. Now, you don't have to have IBIS models. Like I mentioned before, I could go select a completely different net here that doesn't have a model assigned to it, more than likely. Come up here, we'll see, whoops. We'll see that there's no model assignment. Well, actually, everything came across from the schematic, so it's kind of unfair. But I could come in here and select, and I could just do the simple, you know, the CMOS 3.3 volt fast, ultra fast scenario and simulate that net and get some idea based on what my data sheet says, whether or not I think I'm going to have a problem. Okay. So let's go back to our presentation here. So as I've mentioned already, don't wait until the layout starts. As an engineer, you can do a lot of things in a what-if scenario, playing around with net length, board stack-up, receivers, driver strength, termination schemes. A big one too is defining or creating what you think your length rules need to be that you would put into your design. Verify all your critical nets up front. You should know just from the parts you've picked, looking at the data sheets, look at the slew rates, make sure you understand that, and verify those devices, okay? And then of course at the very end, even though after the board layout's been done, you may not be the guy that's doing the actual board layout. You may have tried to convey as much as you can to a services company in what to do in the design, but they may not follow everything that you've suggested. So bring the board back in. You can do simple verifications using a batch process in the board sim tool. I can run, check every single net on the board actually very quickly and find those ones that are suspects and then go back and check them individually. And again, we can play around with termination, adding termination on the fly to see if that's a viable solution. So before I produce that first board, I want to make sure that I'm not going to have any SI issues. And I've seen many customers actually go off and do this and have their boards turn out perfect the first time just because they spent a little time and did simulation up front. Another place where quick simulation like this can help out is over engineering. A lot of data sheets or manufacturers may suggest you do things that may not apply to how you're using the part on your board. Maybe the traces are going to be longer than what they're showing in their reference designs. Maybe the board materials they're using are different, or they're specifying board materials that may be too expensive and you don't want to use them. So you won't know how it's going to affect things unless you play around inside of a simulation tool. Buying parts that are not mainstream. Maybe you're trying to find a device that has slower edge rates, but it's not something that's readily available and it costs more money because it's older technology. So if you buy a more mainstream part and just deal with or play around with doing free things in the board like stack-up, it don't cost much money, can fix your problems, okay? So again, don't over-engineer your designs. Take advantage of simulation tools. Most people wouldn't go off and just throw together an analog circuit. A lot of times that's somewhat complex. They would simulate that, or RF circuits. They would simulate those objects or designs and then move into physical layout. You should do the same thing for any board that's got digital signals on it, because you don't know what you don't know, basically. Okay. Checking SI can be very easy. Again, with increasing device speeds, you may end up with signal integrity crosstalk problems. If you do nothing, doing nothing is basically not an option anymore. I've pretty much conveyed this message very heavily in this presentation. You should always be looking at signal integrity. Simulation tools are readily available. If it's not from Metagraphics, there's a lot of other people out there that have SI tools as well that you can use. There may be some tools that came with your product that you purchased, but Hyperlinks is definitely the #1 and easiest to use tool out there. So if you want to do something quick and easy and not have to really learn the detailed principles of signal integrity, look at Hyperlinks as a tool to assist in that tool flow, okay? Some additional products out there that are available as well for things like I mentioned, the power planes are starting to become a bigger and bigger issue. Mentor Graphics has a power plane analysis application for looking at DC drop in your planes as boards get smaller and smaller and you're using denser parts. The amount of copper that goes into the center of BGAs or to these small devices is a lot less than you think. And if you're trying to pull 2 amps into a microprocessor or something, and you only have about 10 mils of copper getting into that device, you're going to have a DC drop in your plane area, and it's going to cause problems. I'll guarantee you 100%. So looking at the plane structures on boards now is becoming something more and more people need to do. And this is very, very simple to do with Hyperlinks. Again, you don't have to be an expert in signal integrity to take advantage of this. And then something new that's coming out, again, Mentor is forging the way. In this space, this tool has been around for a little while now, and competitors are now starting to jump on the bandwagon, but obviously we're leading that space, is electrical DRCs. We all do physical DRCs, but again, now more and more parts these days have higher speed edges, and we don't realize it. And doing electrical DRCs is something that should become more commonplace in your design flows. So doing some quick EMI checks, power distribution checks, basic signal integrity things can all be checked very quickly with this tool. It's like you visually going in and analyzing your board inside of a layout tool or a viewer. That can take a lot of time. And doing visual inspection is error prone as well. Where this tool, again, very simple to set up rules. It comes with like 22 rules, I believe. We actually have a free version of this tool coming out very soon here around the end of the month. That's going to have a basic set of 8 rules with it that any of you out there can use for free, online based. And please look for that and take advantage of that. But if you need more detailed verification, Hyperlinks DRC can assist there. And then for all of those doing DDR, we have special version capabilities in Hyperlinks that I've shown you already that are geared strictly towards DDR verification. Many of you out there probably know it, but there's probably a lot of you that are trying to do DDR on board and just going off specifications. And it can work in some cases, but a lot of times, again, you don't know what you don't know. And if you're not doing some type of verification on those DDR channels, you may not get it right the first time. And any spinning of a board costs money and could easily pay for a tool that you'll just be able to use over and over again as time goes on. So. All right, so that is the end of our presentation. I want to thank you everyone for joining us today. Again, remember we have our next one's coming up on November 9th. Please look for that on our Oasis website, or we'll be sending out invites as well to that. And then again, don't be afraid to give us a call. If you have any questions about these applications, if you'd like me to come on site and visit you, we can talk about these in detail more in person. As well, I'll be happy to assist there as well. All right. Well, thank you again, everyone, for joining. And please visit our YouTube channel. Look for Oasis Sales on YouTube for this webinar and others that might be of interest. Thank you. Goodbye.